Surviving in the vacuum of space without a spacesuit is an alarming concept that underscores the extreme conditions of space travel and the fragility of human physiology. Understanding what happens when humans are exposed to the near vacuum of space reveals critical insights into both the risks of space exploration and the robustness of the human body. When exposed to the vacuum of space, the immediate and most vital rule is not to hold your breath. The reason for this is that in the vacuum, the air inside your lungs would rapidly expand due to the lack of external pressure. This expansion can cause your lung tissues to rupture, leading to fatal injuries. Therefore, if you find yourself in such a situation, the most important thing is to exhale to avoid this catastrophic injury. In the vacuum of space, you would initially have about 10 to 15 seconds of consciousness, though the effectiveness of this time window for meaningful action is limited. During this period, you might experience severe physiological effects, such as ebullism, where bodily fluids begin to vaporize due to the reduced pressure. This process can lead to swelling and severe discomfort. However, it is crucial to note that even though you might remain conscious for a short time, the environment is so hostile that any potential for survival hinges on rapid repressurization. The critical survival window for repressurization is based on a combination of historical incidents and scientific experiments conducted on animals. These studies provide insights into the human body's reaction to near-total vacuum conditions. For example, in the 1960s, Brooks Air Force Base in Texas conducted a series of high-altitude experiments on dogs to study the effects of exposure to low-pressure environments. In these experiments, the dogs were subjected to conditions equivalent to 1/380th of normal atmospheric pressure. The results were quite revealing. As long as the dogs were repressurized within 90 seconds, they generally survived without significant long-term damage. Prolonged exposure beyond 2 minutes, however, led to severe consequences, including cardiac arrest and death. During these experiments, the dogs exhibited a range of distressing symptoms. Within 10 to 20 seconds of exposure to the vacuum, the dogs lost consciousness. Simultaneously, they experienced uncontrollable urination, projectile vomiting, and defecation, which were attributed to the rapid expansion and subsequent expulsion of gases from their digestive systems. Additionally, some of the dogs suffered from seizures and displayed a thin layer of ice forming on their tongues due to the rapid evaporation of moisture, which caused a dramatic drop in temperature. Despite these severe symptoms, if repressurization occurred within the critical timeframe, the dogs' swollen bodies, often described as resembling inflated goatskin bags, would typically return to normal, with no apparent long-term harm. Human experiments provide further context, though direct experimental data are limited due to ethical considerations. However, studies involving chimpanzees, who share many physiological characteristics with humans, offer valuable insights. In tests similar to those performed on dogs, chimpanzees were exposed to vacuum conditions and were found to endure up to 3 minutes without enduring long-term cognitive impairments. This evidence is consistent with some human accident reports. For instance, in a 1965 incident at the Johnson Space Center, a technician accidentally depressurized his spacesuit. He remained conscious for 14 seconds and felt the moisture on his tongue evaporating. Fortunately, repressurization was quickly initiated, allowing him to regain consciousness within 27 seconds. He experienced only a temporary loss of taste, which returned within a week. Despite these relatively positive outcomes, not all vacuum exposure incidents have ended well. Dr. Emanuel M. Roth documented a case in 1968 where a man exposed to vacuum conditions for about 3 minutes could not be revived even after repressurization, highlighting that the 3-minute mark represents a critical threshold for human survival in a vacuum. This underscores the importance of swift repressurization and the limits of human tolerance to such extreme conditions. Exploring cases where only part of the body is exposed to space provides additional insights. For instance, during Joe Kittinger's record-setting skydive from 19.5 miles in 1960, his pressure glove malfunctioned, leading to exposure of his hand to near-vacuum conditions. Despite significant swelling and pain, the hand recovered fully within a few hours after landing. Similarly, in 1991, an astronaut aboard the Space Shuttle Atlantis experienced a small puncture in his glove during a spacewalk. This puncture, caused by a palm restraint puncturing the glove's pressure bladder, led to a painful red mark, but the astronaut remained unaware of the incident until after the spacewalk and experienced no long-term effects. These accounts illustrate that while media portrayals of vacuum exposure often dramatize the effects, the reality is that humans have a brief but critical window of time during which survival is possible if immediate actions are taken to restore pressure. However, the risks of space travel extend beyond just exposure to a vacuum. Long-term space missions involve additional challenges such as microgravity, radiation exposure, and psychological stress, all of which impact astronaut health and performance. Microgravity, or the condition of near weightlessness experienced in space, affects the human body in various ways. Prolonged exposure can lead to muscle atrophy, bone density loss, and fluid redistribution, which can impact cardiovascular health. For instance, astronauts in space often experience a condition known as space adaptation syndrome, which can cause symptoms such as nausea, dizziness, and disorientation. Additionally, the lack of gravity affects the cardiovascular system, leading to changes in blood volume and pressure that can result in orthostatic hypotension, a condition where astronauts feel lightheaded or faint when standing up. Radiation exposure is another significant risk. Space is filled with high-energy particles from the sun and cosmic rays that can penetrate the spacecraft and human tissues. Prolonged exposure to this radiation can increase the risk of cancer, damage to the central nervous system, and other health issues. NASA and other space agencies take extensive measures to shield astronauts from radiation, but the risk remains a concern for long-duration missions, such as those planned for Mars. Psychological stress is also a critical factor in long-term space missions. Isolation, confinement, and the absence of natural environmental cues can affect mental health. Astronauts are subject to rigorous psychological evaluations and support systems to help manage stress and maintain psychological well-being during missions. Overall, the challenges of space travel are multifaceted, encompassing physical, psychological, and environmental factors. While brief exposure to a vacuum might be survivable under certain conditions, the broader context of space travel highlights the need for continued research, advanced technology, and comprehensive health measures to ensure astronaut safety and mission success. The lessons learned from experiments and accidents continue to inform safety protocols and improve our understanding of how to protect human health in the extreme environment of space. It's important to note that while the human body is remarkably resilient, the conditions of space are incredibly hostile. The risks associated with space travel are significant, and ongoing research is essential to mitigate these challenges and ensure the safety of future astronauts. As humanity advances toward longer duration missions and deeper space exploration, the protection of astronauts from the vacuum of space will be a paramount concern. Future technologies and innovations will likely focus on developing highly resilient spacesuits and spacecraft that can offer enhanced protection against the vacuum, radiation, and microgravity. Advanced materials with greater tensile strength and flexibility will be crucial in creating suits that can withstand the harsh conditions of space while allowing astronauts to perform their tasks effectively. Additionally, smart systems integrated into the suits will monitor vital signs and environmental conditions, providing real-time data to prevent accidents and enhance safety. Innovations may also include self-sealing mechanisms to quickly address breaches and automated repressurization systems to minimize the risk of exposure. The integration of artificial intelligence and machine learning will further optimize emergency response protocols, ensuring rapid and effective action in the event of a vacuum breach.